Hello and welcome to today's lesson. We're going to be talking about sample spaces. So that means we're going to be looking at how to calculate how many different outcomes can happen in a situation such as rolling a fair die twice and flipping a coin twice. How many different outcomes can there be? And once we get that down, then we're going to be looking at how to calculate probability, which uses the skill of finding the number of outcomes. So as we're going through that and learning that, please make sure that you are taking notes. If I ever go too fast, just pause and rewind so you can get caught back up. And that way you have those notes so that you have them to refer back to when you are studying and trying these problems on your own. And you don't have to rewatch the video to get those answers and help. So I'm so glad that you are joining us today, and let's go ahead and take some notes.
There are two counting principles that can help us out with these problems. The addition principle of counting states that for two mutually exclusive events, so there's no common outcomes or pieces, so they don't have anything to do with each other, the total number of possible outcomes can be found by adding the number of possible outcomes from each event. The counting principle of multiplication states that if there are A ways that the first event can occur and B ways that the second event can occur, then there are A times B ways that both events can occur. So you're going to multiply the two numbers. And we'll look at examples that use both of these to help. So you can use tree diagrams to help you find a probability, or just to find out the number of outcomes, depending on what the question is asking. So here is a tree diagram for the toss of a coin. So you have two branches. When you toss a coin, you can get heads or you can get tails. And then you're going to write the probability of each branch on that branch. So when you flip a coin, you can get heads 1 out of 2 times, or you can get tails. The probability is 1 out of 2 also. And so that gets written on the branch. We can extend the trigram to 2 tosses of the coin. So if you toss a coin twice, so when you do that, you're either going to get heads or tails the first time, so that first part stays the same, and then you're going to add a second layer of branches here for the second toss. So the second toss can also get heads or tails. The second toss can also get heads or tails here. Each time you flip the coin, though, that probability of 1/2 or 0.5 stays the same. So that's why you write that 0.5 on each of these branches. So how do you calculate the overall probabilities? Well, you multiply probabilities along the branches and add probabilities down the columns. So to find the probability of flipping heads twice, you would multiply down the branch. So 0.5 times 0.5. And so all probabilities should add to 1, because the probability of everything happening is 1. 1 is 100% chance. So here, the probability of getting at least 1 head from 2 tosses, well, if you go here, you have head, here you can get a head at least once, here you can get a head at least once, and here you can get a head at least once. So since you're going down the column, you would add these. And so the probability of the 2 tosses, they already multiplied them here. You would add these 3 up, and that's where they got the 0.75. And just as a check, if you add up all 4 of those, you get 1. This first example says, at the beginning of each school year, every grade level must choose 3 people to work on the yearbook project. A photographer, a writer, and an editor must be chosen. No student is allowed to hold 2 positions. If the 8th grade class has 36 students, how many possible outcomes for the yearbook staff are possible? In this example, I would just like to put that there is a photographer, a writer, and an editor. So I'm just going to draw a picture like that to help me out. So for the first position, there's 36 students to choose from. But since you can't have duplicate students serving for 2 positions, that means when I go to pick a writer, one of those students already has a position. So I'm left with only 35. And then when I go to pick an editor, since 2 of those students are already holding positions, I only have 34. And so then I'm going to have to multiply those 3 numbers using the multiple counting principle. And when I multiply 36 times 35 times 34, which you're welcome to do on the calculator, you're going to get 42,840 different ways those students could be picked for the positions. And so that's going to make my final answer here B. This next question says Dana needs to make a 4-digit code for her safe. If no numbers can be duplicated and 0 cannot be used, how many possible codes can she create? So I'm going to draw 4 blanks, one for each number. And 1-digit numbers, 1 through 9, I have 9 possibilities because it says I can't use 0. So that first number, I have 9 different possibilities I could use. Then my second number, since they don't want them duplicated, I've already used 1 number, so that means I have 8 numbers left to choose from. My third number, we've already used 2 numbers, so that means I have 7 numbers, 1 through 9, left to choose from. And then for my fourth number, I'm going to have 6 numbers left to choose from. Here, I'm going to multiply these because the choices for each of these numbers is dependent on the other one. So that means I'm going to use the multiplication counting principle. And when I multiply 9 times 8 times 7 times 6, that's going to give me 3,024 different codes that she could use for her safe. And so that's going to make B my final answer. Here, Greg is ordering a breakfast. He can order an early bird plate that has eggs, a meat portion, and a bread portion. There are 3 different ways the eggs can be cooked, 3 different meat portions, and 3 different bread portions. He could also order a short stack or tall stack of pancakes. Both of the short and tall stack can be ordered with one of 7 side orders. So how many different breakfasts are available to Greg to order? So I'm going to start to just draw a little bit of a picture to put all of this into, to help me organize the problem. So I have either the early bird plate or he can get pancakes. So those 2 options don't have anything to do with each other. So that means I'm going to have to add, at the end, I'll add their total number of outcomes together because they have nothing to do with each other. That's the adding principle. So for the early bird plate, he has an egg option, he has to choose a meat option, and he has to choose a bread option. So there are 3 ways that he can choose his eggs, 3 ways that he can choose his meat, and 3 ways he can choose his bread. So since that's all one meal, those numbers are related, we're going to multiply them. So that means if he gets the early bird plate, he's going to have 3 times 3 times 3, which is 27 different ways that he can order that. Now, when he does pancakes, he can either do the short stack or the tall stack. And for each of those, he can pick one of 7 sides. So since there's 7 sides with the short stack, that's 7 different meals he could get. And since there's 7 sides with the tall stack to choose from, there's 7 ways he could get that meal also. So pancakes, if he orders the pancakes, there's 14 different meals he could get there. So to get the total different kinds of breakfasts that are available to Greg to order, I'm going to have to take 27 plus 14, which is 41. Which means that A, 41 is going to be your final answer. And this question here says, in a marathon, how many different ways can the gold medal for first place, the silver medal for second place, and the bronze medal for third place be awarded if 18 athletes are running in the marathon? So I have first place, second place, and third place to award. First place, if there's 18 athletes, there's 18 different athletes that could win that medal. Now, once one athlete's awarded this gold medal, there's only 17 left to get the second or to get the silver medal. So that's going to be 17 there. And then after the first and second are awarded, there's only 16 athletes left to be awarded this bronze medal. And so since these athletes are all being awarded medals, they're related to each other. So they're going to have to multiply these numbers to get the number of outcomes. And so 18 times 17 times 16, and you can use your calculator for that, is going to be 4,896 different ways that athletes could place in this race, which is going to make letter C my final answer. This question here says a parking lot has a row of 8 parking spaces, each with a different car in it. How many different ways can the 8 cars be arranged in the parking spaces? So when you look at the answers here, you notice that the answers have an exclamation mark in them. And so that isn't that you're reading the number with emphasis. An exclamation mark in math means the factorial. And what a factorial is if you have, let's say, 4 factorial, that's the same as taking 4 times 3 times 2 times 1. So it's multiplying together all of the number that you're given times all of the numbers less than it also. So 6 factorial would be 6 times 5 times 4 times 3 times 2 times 1. And so we have these 8 parking spaces. And so I'm just going to draw a line for each of those 8 parking spaces. So I can write on the line the number of choices we have for those parking spaces. So the first parking space, there's 8 cars to choose from. So there's 8 different cars that could park in that first spot. So one of those cars is now parked. So that means in the second spot, I have 7 left to park there. So now I have 2 cars parked. That means in my third spot, I have 6 choices of cars to park there. Now there are 3 parked, so that means I have 5 cars left to park in the fourth spot. I have 4 cars parked now, so I have 4 cars left to park in the fifth spot. Now there are 5 cars parked, so I have 3 left to park in the sixth spot. Then I'm going to have 6 of these cars parked, so there's only 2 left to park in the seventh spot. And now there's 7 cars parked, so there's only 1 left that could park in that last spot. And since these cars are related to each other, they're all parking in the same spot, I'm going to multiply these numbers together. And when I look at it, I see that my answer here is the same as what 8 factorial represents. I'm taking 8 times every number less than it. And so that's going to make letter A my final answer. In this problem here, they've already drawn a tree diagram for us. And it's a tree diagram that shows an experiment consisting of flipping a fair coin and rolling a fair die. How many possible outcomes have an odd number? So here I have, you flip a coin and you can get heads or tails. And then you roll the die and you can get 1 through 6. So that's how they built this. And there's no probabilities on this one because it's just asking about the outcomes. It's not asking about the probabilities. yet. So it wants to know how many possible outcomes do we have with an odd number. So here's a 1, 3, and 5. There's my odd numbers if I roll a head and roll a die. And then if I flip and roll a tails and roll the die, there's my 3 choices with an odd number. So here I have 1, 2, 3, 4, 5, 6 outcomes that involve an odd number. So it's going to make letter B my final answer. In this problem here, they give us a scenario and want us to match it to the correct tree diagram. So the scenario is a two-sided coin with heads and tails is flipped 3 times. Which of the following tree diagrams represents all the possible outcomes of the coin toss? So that means that when I'm working on my tree diagram, I'm going to have heads and tails flipped, and then I'm going to have heads and tails flipped again for each of those outcomes. And then for each of these outcomes, I'm going to have heads and tails flipped again. So I'm looking for one that has, for a tree in my answer here, that has it 3 times down a branch. In choice W here, I'm looking and there's 1, 2, 3 in the branches. However, if I look at my last branch here, it's only saying that if I were to get heads the first time, heads the second time, then I'm definitely going to get heads the third time. It doesn't have this split here on heads that you need. So you have to have that split for heads and tails for each of the 3 branches. And so then it can't be W. Okay, for X here, if I go down a branch, I have 1, 2, 3, 4. So here they did 4. They flipped the coin 4 times, so it can't be X. And Y here, I have 1, 2, 3, and it looks like each time they did the split for heads and tails, they showed it heads and tails for each time the coin was flipped. So it most likely is going to be Y because they look similar here. And then Z, if I look, it only goes twice. They only did it for 2 flips, so it can't be Z. So that means Y is going to be my answer, which is choice A. This question says Jolie has 3 types of DVDs and 2 types of CDs as shown above. So they've already drawn the tree diagram for you. If she grabs a disc at random, what's the probability that it is a DVD or a rock CD? So probability is the number of successes over the number of outcomes. So first we're going to look at the number of ways that you can get a DVD or rock CD. So here we have a DVD. You can get 3 of those, and get a rock CD, there's 1 of those. So total, there's 4 different ways to get a DVD or a rock CD. And that's going to go over the total number of outcomes. And so total number of outcomes is 1, 2, 3, 4, 5. Looking at the last row in that tree diagram, lists all of the total outcomes. And so that means my probability here is going to be 4 out of 5, which is choice A. This question here says Rom draws a card from a standard deck of playing cards 3 separate times. What is the probability that he draws a club on the first draw, does not draw a club on the second draw, and does not draw a club on the third draw? Use a tree diagram to solve. So remember, when you have a deck of playing cards, you have the 4 suits. You have hearts, diamonds, clubs, and spades. And there's 52 cards in a deck, and so each of those 4 suits is going to have 13 cards. So if you add 13 plus 13 plus 13 plus 13, or 13 times 4, that gets you to 52. So there's 52 cards in a deck, 13 cards in each suit. So the first thing he does is draw a card. And so when he draws that first card, he could either get a club or not a club. And so that's what the first part of your tree diagram is going to look like. And you can draw it going up and down or left or right. It doesn't matter. So I'm going to go ahead and write the probability of drawing a club and the probability of not drawing a club on that first draw. So there's 52 cards I could pick from. 13 of them are clubs. So I have a probability of 13 out of 52. Then I have 3 suits left over that aren't clubs, so 13 plus 13 plus 13 is 39. So I have 39 out of 52 cards that is not a club. So that's my probability of drawing not a club on the first draw. So then he draws another card and he's looking to see whether or not it's a club. So that means for each of these outcomes here, I'm going to draw another 2 branches off of those. In each one of those, I could get a club or not a club. So I draw 2 more branches off of each of those outcomes. And I have to find the probability of each of those. So now I've drawn a card. Here, there's only going to be 51 cards left to draw from. So looking at my first scenario where I already picked a club, if I picked a club a second time, that means one of my clubs is already gone from the first time. So that means I only have 12 left to pick from out of that 51 cards. So 12 out of 51 is my probability. Now, if I picked a club the first time and then picked no club, that means out of the 51 cards, I still have 39 that aren't clubs. So that means my probability of picking no club the second time is 39 out of 51. So now I look at calculating the probabilities if I selected no club. So if I didn't select a club the first time, that means I still have all 13 of them to pick from the second time out of that 51 cards. So my probability is going to be 13 out of 51. And then if I picked no club the first time and no club the second time, that means I'm down to 38 cards that aren't clubs out of 51, and that's going to be my probability the second time. And then the last thing I have to do is the tree diagram for if he doesn't drawing a card a third time. So that means after each one of these outcomes, I have to draw 2 more branches from each one of those showing club and no club. Like that. And then I have to write down the probabilities of each one of those. So here, if I drew a club the first time and the second time, that means that there's only 11 clubs left to pick from the third time out of 50 cards now. So that's going to be my probability for here is 11 out of 51. And now if I picked 2 clubs the first 2 times, that means I still have all 39 cards that aren't clubs left in my deck. So I have a probability of picking 39 out of 50 of those on this part here. And so you're going to go through and figure out that third probability for all branches here, and you're going to write them. And when you get done with that, it's going to look like this. And so now we just have to see which branches we want here. So he wants the probability that he draws the club the first time. So that'd be this one. Then the probability that he does not draw a club the second time. So that would be this one. And then he wants the probability that the third time he also does not draw a club. So that would be this one. And you multiply these as you go down the branches. So that means I'm going to multiply 13 over 52 times 39 over 51 times 38 over 50. And when you do that, you get 247 over 1700 as your final answer, which is choice B. And you can feel free to use a calculator to multiply those fractions. This last question says, an urn contains 7 brown marbles and 3 green marbles. Vincent takes out a marble 3 separate times. What is the probability that he takes out a green marble the first time, a brown marble the second time, and a green marble the third time? Use the probability tree to solve. So here, you could do it the way we just did the last problem using the probability tree, and I'll show you what that would look like in the end so you can see it, and you can pause and try that on your own. But you can also just think of what the probabilities would be for those 3 steps and multiply them together. So what is the probability that he takes a green marble out the first time? Well, there's 3 green marbles out of a total of 10 marbles, because 7 plus 3 is 10. So the probability of drawing a green marble the first time is 3 out of 10. So then what is the probability that a brown marble a second time? Well, he picked out a green marble, so that means there's still 7 marbles left in the bag. But since he already took one of those marbles out, there's only 9 left. So it's a 7 out of 9 chance of picking a brown marble. And then the last one is the green marble a third time. So he already picked a green marble out. So that means there's only 2 left. So there's 2 left and 2 marbles are gone. So there's 8 total marbles left. So that means 2 out of 8 is your probability. And so then you just multiply those 3 fractions together, either multiplying all the tops and all the bottoms and reducing, or you can use a calculator. Either way, you're going to get an answer of 7 over 120 as your probability, which is choice A. Now, if you wanted to do a tree diagram, your tree diagram would look like that, and then once you fill in all of the probabilities, it's going to look like this. And you can see that you end up multiplying the same 3 numbers together to get the same answer. Either way you do it, you're going to get the right answer. Just pick the way that works for you. Thank you for joining us today, and I hope you learned something new.